So here are the three results again. The first isomorphism theorem, the correspondence theorem, and the third isomorphism theorem. The second one has gone missing, but you'll find it in the exercises. I want to go through, at least sketch the proof of the third isomorphism theorem. The first one, once more, says the following. Look at this picture. You have a surjective ring homomorphism from a ring R to a ring S called psi. That's what you start with. Once you have a surjective ring homomorphism, you can look at the kernel of the homomorphism. It's called I, let's say. Once you have an ideal, so I is going to be an ideal in R because kernel of a homomorphism is an ideal. You can construct the quotient ring R mod I, and you have a homomorphism called the quotient map from R to R mod I. Again, double arrow. Double arrow means surjective map. So that's the setup. The theorem says that given all this, there exists a unique isomorphism from R mod I to S. So in particular, R mod I is isomorphic to S. It also tells you what that isomorphism is. It says that if you start with an element A in R, if you go down using pi, you're going to go to the coset. That's what pi does, takes an element to its coset. Applying eta to such a thing is same as applying psi to A. These two things are the same. My arrow doesn't land in the right place. So going down right and then up right, same as going right. Okay. The correspondence theorem says that when you have a ring R and an ideal I, take the quotient map R to R mod I. The cartoon is on the right side. This sets up a bijection between the ideals of R that are above I, that contain I, and the ideals in R mod I. So if you give me an ideal in R that contains J, I can apply pi to those elements, and the image will be an ideal in R mod I. Conversely, if you give me any ideal in R mod I, then I take pi inverse of that. If you give me an ideal here, then I'll take all the elements in R that go into K under pi, and that's going to be an ideal in R that is going to contain I. And this sets up a one-to-one correspondence. It tells you that when you apply quotient homomorphism, you forget the structure inside I, but you retain the structure, the ideal structure above I. The third isomorphism said, down here, that when you have two ideals, I and J, so you have R, you have an ideal in there, and then you have a smaller ideal of R in there. You could go to R mod I, and then J determines an ideal in there called J mod I. And I itself becomes I mod I, which becomes just the zero ideal of R mod I. And it says that this quotient, R mod J, is same as that quotient. So R mod I mod J mod I is same as R mod J. That's the statement. Okay. And if you want to argue this, what you have to say basically is, let me give a sketch here maybe. There isn't a whole lot to say. By the way, the correspondence theorem I did not prove. I'm just leaving that as an exercise, I suppose. It's pretty straightforward. So this one will be an exercise. The first one we have proved in detail Here is a sketch of proof of the third one. I need to prove R mod J is isomorphic to R mod I mod J mod I. So the philosophy is that you want to get a map from R mod J to the thing on the left hand side. But you don't want to directly define these maps because it's going to be elements of R mod J, remember, are these cosets. So defining maps on those is kind of cumbersome and not elegant. So what you want to do as far as possible is you want to define a map from R rather. And then use the first isomorphism theorem to factor through R mod J. I mean, the thing is, if you get a homomorphism from R mod J to something, then you are also going to get a homomorphism from R to that thing, because in any case you have this quotient map from R to R mod J. So if you give me a function f from R mod J to some creature, I can just apply pi first and then apply f, and then I get a map from R to that creature. So in any case, if you want to construct a f here, you might as well construct a map here. Okay, that's the philosophy. So what I'm going to do is I'm going to start from R. Consider the maps. I should say rather the homomorphisms. R to R mod J, you have a homomorphism that is sort of God-given. What is it? It's this quotient map. Takes an element to its coset. Sorry, R mod I. Don't want to go to R mod J yet. And from in there, I mod J is an ideal. Sorry, J mod I. I'm messing I and J all the time. J mod I is an ideal in there. Let's call that J bar. It's also same as pi of J. So here is a ring. Here is the ideal in that ring, J bar. So you could further apply the quotient map. So if you are confused about notation, let's call this guy S. And then I can go to S mod J bar, because J bar is the ideal in S. So that's same as R mod I mod J bar. So just for typographic reasons, sometimes I write A divided by B, sometimes I write A slash B, means the same thing, by the way. Okay. So this is also the quotient map. Let's call that pi prime. So pi and pi prime quotient maps. Right. And again, J bar is same as J plus I. J mod I. So I can go from R to this R mod I mod J mod I in 2 steps. Apply 2 quotient maps back to back. So if you apply them back to back, first apply pi, then apply pi prime, then you have a map now from R to R mod I mod J mod I. So consider the composition. The claim is that what you need to check, this is where you have to do some work, is that the kernel of this guy is, have you guessed it? It's J. And once you prove that, then you are done by first isomorphism theorem. This is onto, because quotient maps are onto, so this one is onto. You have a surjective ring homomorphism from one ring to another ring. The kernel is J, So that induces an isomorphism from R mod J to this guy. And here also you have the standard quotient map. So all that I need to check is this claim. But that's, once you have set it up like this, it's almost a tautology. So you have to just unpack what these maps are. You give me so let's just do it in this picture, even though this picture is kind of becoming messy. It's a good idea to, as they say, chase these diagrams and figure out what's going on. So if you give me an element in J, that goes to its coset, call it J bar. And that coset belongs to the image pi j, J mod I. It's a coset of represented by an element of J. So this belongs to what I call J bar or J mod I. And then when you apply pi prime to that guy, when you go down and right, it goes to J bar plus J bar. This quotient map is taking quotient modulo J bar. So it takes J bar to little j bar plus capital J bar. But since little j bar is in capital J bar, right here, this is same as J bar, which is same as the 0 of this ring. Let's call this ring T. Then it's the 0 of T. What did I just say? I said that if you take something in J, then it goes to 0 when you apply pi and then pi prime back to back. So I proved this inclusion, that J is in the kernel. And the other inclusion is almost as straightforward. Yeah? So check the rest. I mean, it's much better to do these arguments yourselves than to follow someone else's thinking. Yeah. So the rest. So I'll just say claim exercise. Once you know that, then by fast isomorphism theorem, we get that R mod. Let me just draw the picture for you again. I have R mod I, mod J mod I, and I have this map pi prime compose pi, and the kernel of this is J. That was the claim. So first isomorphism theorem says that when you have that, and if you take the quotient map here, call it pi double prime. I don't want to call all these maps pi. They're different quotient maps. Then you get isomorphism from R mod J to R mod I, mod J mod I. Says that going down, going up is same as going right. In particular, these two rings are isomorphic. And that's the third isomorphism theorem on the left here. Okay. So So next time we'll talk about prime ideals and maximal ideals.